confidence intervals are my favorite part about the midterm because they're probably some of the more straightforward questions to do. The question's going to explicitly ask you for a confidence interval, okay? And so what a confidence interval is going to do is once we calculate it, it's going to give us an estimate of what the real mean might be. And so it's not going to calculate the actual mean, but we're going to go out and we're going to get some sample data. And from that sample data, we're going to be able to estimate this interval, okay? So we're going to be given a sample statistic. Pre-midterm, it's just sample mean, and you can calculate the upper or lower bound of the confidence interval. So the confidence level, and often you'll see something like the 95% confidence interval. So that confidence level is 1 minus alpha. So if it's a 95% confidence interval, that means that alpha is 5%. That's the proportion of intervals that actually contain our true mean. So just because we come up with an interval, let's say like the one I wrote above, 15 to 17, does not mean that the mean is actually between 15 or 17. If that is a 95% confidence interval, then 95% chance that the real mean is somewhere between 15 and 17. So there are lots of different confidence intervals, but they all come in the same form. It is the test statistic plus or minus either the z or the t-value times the standard error. And if we remember, all of our transformations, like the z transformation I have written out here, they are the test statistic, that would be our x bar, minus the mean, over, and that entire denominator is the standard error. So really all a confidence interval is a rearrangement of this formula to solve for the mean when we have both a positive and a negative value for the z value. So when we're looking at a let's say, again, 95% confidence interval, if we're in the situation where this is our Z transformation, meaning we're in boat number 1, we've got population standard deviation, and we are talking about a sample mean, and we have no population size, no big N, our confidence interval formula is going to be that test statistic, so X bar, plus or minus, this has a Z value, so it's going to be Z of alpha divided by 2 times the standard error, and the standard error is just the denominator of that Z transformation. So the only thing we actually have to do for confidence interval formulas is calculate what the Z value or the T value is. And what we're going to do in that is find it using our reverse lookup. So if I'm looking at the 95% confidence interval, what I'm talking about is that 95% of the probability is contained in the middle, meaning that 2.5% would be in each tail, or alpha divided by 2. We're always going to divide it by 2. It's always symmetrical. And so to come up with the Z value that marks the spot, it's going to be symmetrical. So on one side it's positive and on the other side it's negative. It's why we have this plus or minus in our formula. So to come up with that Z value, our Z of alpha divided by 2, which in this case might be Z of 2.5%, this is going to be a norm dot S dot inverse of 2.5%, and that's going to give us our value that's going to go into our formula. So that's the only one that we're going to have to actually calculate for confidence interval, and then it's just about utilizing our formula. So just to wrap our heads around this whole 95% confidence, the idea is that we are going to start with X bar, whatever X bar might be, okay? Then we estimate the max and the min. And whatever the real mean is, that mean is still the true mean. Let's say that mean is, as per this diagram, 0.75. And so a 95% confidence interval means that 95% of the time, right, there's a 95% probability, or 1 minus alpha probability, that the true mean is in our interval. And so that means that there's an alpha percent chance that our interval did not contain the mean. And so every interval that we come up with is either going to contain the mean or not contain the mean, but the chance that it does is going to be whatever our confidence level is. So since we are just rearranging our Z or our T transformation, we have the same three situations as we have for sampling distributions that apply to our confidence intervals. So for the first one here, this is just us transforming that formula of x bar minus the mean over standard deviation divided by root n to get to our confidence interval formula. For the second one, that is when we need the finite correction factor, so x bar minus the mean over sigma divided by root n, and then we've got that n minus n over n minus 1. And for the third situation, it is a rearrangement of our T transformation, which is just S over root n in our denominator there. And so again, I like to refer to these as situation 1, number 2, and number 3 for clarity. And we don't have to rearrange them each time. We can use the formulas that are provided to us, but the rationale for which formula applies is going to be the same as if we were doing sampling distributions. So we're in situation number 1 when we have our population standard deviation and sample size over population size is less than 5%, or of course they just don't give us the population size at all. There's no big N given. We're in situation number 2 if we have the population standard deviation and that sample size is more than 5% of our population. This is where we need our finite correction factor. And remember, that extra term, that's just the finite correction factor there. And if we have our sample standard deviation instead of population, this is when it is the T distribution instead of the normal distribution. And you'll see that 3 and 1 look exactly the same, except that we're using the T value instead of Z, and we have S, which is our sample standard deviation, instead of sigma, which is our population standard deviation. In all three of these situations, the main thing that we're going to have to do is find our Z or our T value. And these are always going to be using our inverse functions. If it's a Z value, the simplest way is a norm.s.inverse, and you just plop in that tail percentage, which is going to be half of whatever your alpha is. And if it's your T, that is a T dot inverse, but we also have to give it the degrees of freedom. That's what that second term is there. And we have our degrees of freedom here going to be n minus 1. And so if we take a look at the example, the main thing that we're going to have to do in any of these problems is identify which situation we are in. So question 1, an industrial designer wants to determine the average amount of time it takes an adult to assemble an easy-to-assemble toy. A sample of 16 items yielded an average of 19.92 minutes. So we have a sample, so our n is 16. The average time, so that's our x bar, is 19.92 with a sample standard deviation. So S is 5.73, our sample standard deviation. And as soon as we have sample standard deviation, that means that we are dealing with situation number 3. We are looking at the T distribution, which means that when it tells us, assuming normality of assembly times, the normality of assembly times just means that our n can be less than 30 and our central limit theorem still applies. Provide a 95% confidence interval for the mean assembly time. So 95% confidence interval means our alpha is 5%, and it's going to, again, explicitly ask us for our confidence interval. And because of that, we know that our formula with our T distribution is x bar plus or minus that T value, which we're going to have to find, and then our standard deviation divided by the square root of n. And so we have everything we need except for that T value. So to find our T value, we want to recognize that with a 95% confidence interval, we're putting 95% in the middle. So that alpha of 5% is getting split into both tails, and because it's getting split, we know that the T value we are looking for is T of 2.5%, and our degrees of freedom, which is just our sample size minus 1, is then going to be 15. So we are looking for T dot inverse of 2.5%. I'm finding the lower tail. We don't actually care if we find the upper or the lower tail here, but 2.5% and our degrees of freedom 15. So that t-value is going to be negative 2.131. And from there, it's just about populating our formula. So our x bar is 19.92 plus or minus that t-value of 2.131. Our sample standard deviation, 5.73, divided by the square root of our sample size, which was 16. And so we go through and we do this calculation once with the positive and once with the negative. When we go through and subtract, we're going to get a value of 16.87. So that's the lower bound on our mean. And on our upper bound, it's going to be 22.97. And so what this is telling us is that we have a 95% chance that the population mean, that the true mean, that mu is within this 16.87 and 22.97. It's not guaranteed, but there's a 95% chance that that range contains our mean. If we take a look at the next example, it says that a sample size of 100 produced a sample mean of 16. So we have n equal to 100, and our mean, x bar, is 16. Assuming the population standard deviation is 3, so it's giving us sigma, which means that we're talking about being in situation 1 or 2. It's going to be a normal distribution. Compute the 99% confidence interval for the population mean. So I want a 99% confidence interval, which means alpha is 1%. And so because we have our sigma and we have no big N, no population size is given to us, we are in situation number 1, where our Z transformation would be our x bar minus the mean over sigma divided by root n, but more importantly than the actual Z transformation is our confidence interval formula. Our confidence interval for the mean is x bar plus or minus Z of alpha divided by 2 times our standard deviation divided by root n. And so what we need to find here again is that Z value. So if we're dealing with a 99% confidence interval, that means that we are putting that 1%, that alpha, split into both tails. So that means that there's a 0.5% in each of our tails here. And to find the Z that goes with that value, where it's going to be negative on the lower end, positive on the upper end, we're going to use our norm.S inverse. So that Z of 0.5% is norm.S dot inverse, and if I'm going to put this in as a percentage, I can put it in as just 0.5 with a percent sign, or if I convert it to a decimal, 0.005. Make sure you don't put in 0.05 like as in 5% there, and this is going to give us a Z value of negative 2.576. And so again, we're getting the negative just because it's the easier one to get. We don't really care whether it's negative or positive because we're going to go plus or minus. So when we populate our formula, the sample average is 16 plus or minus 2.576. Our standard deviation is 3 divided by the square root of our sample size, which is 100, and we're going to calculate the positive, like using the plus, so 16 plus this 2.576 times 3 divided by the standard deviation, divided by the sample size, and then we're going to go minus, and we're going to get our lower bound and our upper bound. So our confidence interval here is 5.23 as our lower bound, and 16.77 as our upper bound. And so that confidence interval is going to tell us that we have a 99% chance, right? There's a 99% chance that the real mean is in that interval. So it's not guaranteed, we're not calculating the real mean, but there's most likely that true mean is somewhere between those two numbers. So question 3 here says that a mutual fund is trying to estimate the return on investment in companies that won quality awards last year. A random sample of 40 companies, so we've got our sample size of 40, was selected, and the return on investment is calculated. A sample mean, so we've got our sample mean is 14.75, and the sample standard deviation, so we've got an S here, of 8.18 was calculated. And as soon as it asks us for sample standard deviation, or gives us sample standard deviation, we know this is going to follow that t distribution. And so that we know then that our confidence interval formula is x bar plus or minus the t of alpha divided by 2 times s divided by the square root of n. And again, the main thing that we have to do here is find the appropriate t-value. It tells us to construct a 95% confidence interval, so that means that alpha is 5%. And so if we're taking that 5%, we're putting that 95% in the middle, 5% is getting split between our two tails, so there's 2.5% in each tail, and we're looking for the t-value that marks the spot. It's going to be symmetrical, one's negative, one's positive, which is why it's the plus or minus the t-value, but we can calculate that t-value. Our t-value of 2.5%, we use our t dot inverse, right? We're using our inverse function anytime we have a probability and we want a value. And so we put in that 2.5%, but the other thing we need is the degrees of freedom. And so our degrees of freedom are always going to be our sample size minus 1. So in this case, 40 minus 1, or 39. And so we're going to put in that degrees of freedom of 39, and our t-value here is going to give us back negative 2.023. And so again, we're just using our Excel functions to get our necessary t-values, okay? And so from there, we're just going to plug into our confidence interval formula, right? We're going to take that mean of 14.75 plus or minus the t-value we just found of 2.023 times the standard deviation, 8.18, divided by the square root of our sample size, and we looked at 40 items here. And again, if we calculate this, we're going to get two values, one when we do the positive, one when we do the negative, and we're going to have 12.14, and we're going to have 17.36, and this gives us our confidence interval, okay? And so that confidence interval, in this case, we are 95% certain, or there's a 95% chance that the real average, the real mean for return on investment is somewhere between 12.14 and 17.36. We look at the next question here. It says you're analyzing the average price of a pint of beer at restaurants in Kingston. The national variance in beer prices was $5 for a pint. So this has given us the variance, which is sigma squared of 5. You want to make sure that you're not going to use that variance when you go to do your calculations, because we are always interested in getting the standard deviation. And standard deviation is just the square root of our variance. It says out of 100 restaurants, you surveyed 30. So this is telling us that the population is 100 and our sample was 30. This is really important because anytime we have a population size, we have to check for whether or not we need the finite correction factor. And so if we check for that, right, our n over n, right, sample size over population size, this is going to give us that our sample size was 30% of our population. This is bigger than 5%, and this tells us that we need the finite correction factor, meaning that we're in situation number 2. And situation number 2 is the fact that our confidence interval formula is x bar plus or minus the appropriate z value, sigma over root n, but then also that finite correction factor. Okay, we're going to multiply that on at the end. So it tells us then that we found an average price of 6.75. So we have our sample average of 6.75, and it asks us for the 90% confidence interval. So if it's 90%, that means alpha is, oops, not 5%, it is 10%. Meaning, again, that we're going to split that alpha into the two tails, so we're going to have 5% in each tail. And so with that 5% in each tail, we can look up the appropriate Z value. Our Z of 5% is going to be our norm.S.inverse, we're using this in Excel, of 5%. I could put that in as 0.05 or 5 with a percent sign, and it gives me a value of negative 1.645. So for our confidence interval now, it's just about populating that formula. The average, our x bar, 6.75, plus or minus, our z value was found to be 1.645. Our standard deviation was the square root of 5. Our sample size is 30, so over the square root of 30, times, and our finite correction factor is going to be 100 minus 30, so population minus sample size, over population minus 1. And if we calculate this out, we're going to get a lower bound of 6.185 and an upper bound of 7.315. And so this is our confidence interval. And so this confidence interval, we have a 90% chance that this confidence interval actually contains the real mean. That's the whole point of a confidence interval. Question 5 here asks us, as the sample size increases, what's the impact to the range of a confidence interval? We want to remember that a confidence interval, generally speaking, is for any test statistic. So it could, we're only doing x bar right now, but it could be p hat, it could be the difference between two means, it could be even a variance or standard deviation, plus or minus, I'm going to say z, but it could be t value, times that standard error. So as n goes up, as n increases, standard error, right? And we want to remember that standard error, something like sigma divided by n, could also be s divided by n. But the main thing here being that that standard error is going to get smaller. Right? As we make the denominator bigger, even though it's under a square root, if we go from a sample size of 10 to maybe a sample size of 100, that denominator, the bottom part, gets bigger, so the whole thing gets smaller. So as n gets big, our standard error gets small, which means that the range is going to get smaller on our confidence interval, right? Because we're going to be adding and subtracting a smaller number, so the overall range is going to be smaller. We can also think about it as the fact that as n gets big, right, we're having a bigger sample size, our information is more accurate. So that range is going to go down, right? There's two ways to kind of conceptualize it, and either way, you're going to be just fine. So for question 6 here, when calculating a 99% confidence interval for the population mean, what is the appropriate t-statistic if a sample, let's just say if not is, if a sample of 40 was used? So if we know that n is equal to 40, and we're talking about a 99% confidence interval, so our alpha is 1%, we are looking for that t value such that we're only putting 0.5% in each tail. And so when it asks us for the appropriate t-statistic, when we calculate that t-statistic, and when it asks us for a t-statistic, other ways it can ask us, it could ask us for the table t-value. It could also ask you for the lookup value. We're using Excel, so we don't actually have to look things up in a table, but that basically means the same thing, that you're using the dot inverse function to find what you're looking for. And so to find that t value of 0.5%, we're going to use t dot inverse. And that t dot inverse, we're going to put in that we're looking for it at 0.5%. And we also need to know the degrees of freedom, which is just n minus 1, so 39. And it's going to give us, because I put in the lower, just that 0.5%, it's giving me back the negative value. So we've got a negative 2.71. Now that's fine. You and I know that we're basically going to use plus or minus 2.71 in our calculation, so it doesn't matter whether we looked up the negative or the positive. When it's talking about the table t-values or lookup values, those values would have been given to us strictly as positive numbers. It would have never given us the negative number in the lookup table. We would have just known that we could use it for negative or positive. So in our multiple choice, if it had given us 2.71, that would have been an acceptable answer. Like, it'll only give you the positive values because it knows that you're going to be looking at using it in a confidence interval where plus or minus, and you know that if it's on the lower side, that you would just add that negative.